Yep, I'm feeling a bunch
To be
of
recorded, but might want just a couple.
skills.
Okay, so let's.
OJ.
I think it's funny that what's his face got married.
That's good.
Mr. Oya.
Yeah, you guys did well. Yeah, you did very well. Oh, it was bad. The music was way too loud.
I know. I could hear it, and I was like, I hope this is the music. I couldn't tell if it's the music or it's everybody else.
It was interesting. It just goes to show like right in the middle of it.
And I'm like, someone's gonna have a seizure. It was bad.
I could actually see why.
The whole audience.
That's where he wanted to go.
Probably.
That's kind of intense.
Okay, so this is what optimization is about. Okay, now the good news is optimization is really, I'm not gonna say it's, I mean, it's a pretty involved process, but you've already done it. The only thing you haven't done is just apply it to situations. All this really is the stuff that you've already been doing with the tables. The difference is that you're gonna be the one setting up the functions that you're gonna optimize based on the situation. Okay, but really that's all you were adding to the process that we've already been doing. So optimization means you're either trying to minimize or maximize a quantity, right? And it's depending on the situation, it could be one or the other or both. In this situation right here, we're trying to determine the dimensions of an open box, and we're told that it's going to have a square base, and it's going to have a surface area of 108 square inches, and we want to determine what the dimensions are going to be in order to maximize the volume. Now I've given you a little recipe here. This is the 5-step algorithm that you use for doing optimization problems. Okay, and it's just kind of always follow this process, and each problem is going to be different depending on the situation, but this is the process that we'll always use. Okay, so step 1 wants us to assign symbols to all given variables and the variables to be determined, and draw a picture. If it's appropriate, draw a picture. In this case, definitely a picture would be helpful. This is going to look an awful lot like related rates. It's the same kind of process that we did with related rates, very similar. Okay, so step 1. What's this going to look like? Well, it's an open box with a square base, and then as we're drawing this, we'll want to kind of add the variables. So there's our open box, right? Okay. You can tell it's an open box because you can see that back corner.
Mm-hmm.
You see how that works? That's kind of a good way to do it. Okay, so what are our variables then? If it's got a square base, what's that telling us?
It's squared.
Okay, so then both of the dimensions of the base, call it whatever you want, we'll call it x. But those have to be the same. Does that make sense?
Yeah.
Okay, and they have to be the same. We don't want to introduce 2 different variables there. And you'll see why as we go along. Okay, what else do we need? We need a height, don't we?
Mm-hmm.
Is the height x?
No.
No. I mean, it's possible that it might turn out to be x, but we don't know that yet, right? The height is where we can freely change the height. And so what we're effectively going to do here is we're going to keep the surface area fixed, and we're either going to kind of squish this thing down so it gets bigger, it gets a broader base, or we pull the top up and it kind of gets to have a smaller square base, because the surface area is fixed, okay? Okay, so there's step one. Step two, write a primary equation. Now, the primary equation is always for it's an equation written for the quantity that we're trying to optimize, either maximize or minimize. And that's always where you want to start here. So ask yourself the question in this problem, what is it we're trying to minimize or maximize? Volume. Okay, so step two then, we've got to come up with a volume equation. Okay, what is it? If it were a sphere,
This is
this is
X
just,
times X times Y.
okay, everybody agree the volume of this thing is just gonna be, this is just a rectangular prism, right? So x squared times y,
Mm-hmm.
volume of or the area of the base times the height, okay? Okay, good. So there's our equation. Now, we're gonna proceed to try to get to a point where we can do the calculus on this, right? We're used to having previously, like in section 3.6, where we were doing all our curve sketching, we either had a y or an f of x for our function, and typically x was the variable, right? Maybe it was t sometimes. When we make our table this time, what's going to be our dependent variable or our function? V, right? So our table is going to have v's. Now, what's the problem with this at this point? V is the dependent variable. That's the function that we're trying to maximize. Does anybody see any issues with this equation that are different than what we had before? How many?
Two.
There's two variables. Okay, that's a problem for us, right? There are two variables, and so how am I supposed to maximize volume if I'm trying to deal with these two variables simultaneously? Really, what this class should be taught, or should be called, is calculus of a single variable. Now, later on in college, you'll deal with multivariable calculus, but for now, that's really not in our repertoire. We only really know how to deal with functions of a single variable. We don't know how to take multiple derivatives, or we haven't gotten to integrals yet. And so we need to pare this thing down to a single variable if possible. If not, we really can't do this problem. So we need to eliminate one of these variables. Now, sometimes we'll be lucky and we won't have two independent variables, and then we can just do the calculus and make our table and be done, right? But this time we're not lucky. This time we've got two independent variables, and so we need what we call a secondary equation. And this is step 3. Okay, so this is our, let me label these. This was our primary equation. And this is our secondary equation. Okay, and a lot of times what people call this is the equation of constraint. And that's actually a really good way to describe it, because it always has to do with the limits or the constraints that are being imposed on the situation. So if there were no constraints on this and you wanted to maximize volume, what would you set the dimensions at? If you wanted to maximize volume and there were no limits, how about just infinity, right? We just make it limitless, big without limit, and then it's kind of a dumb problem, isn't it? That really doesn't have much bearing on what happens in the real world. So typically there is going to be some kind of a constraint placed on this. The constraint is almost always going to be a number, right? There's going to be some kind of a number here that's limiting what we can do. So what's our constraint?
The surface area.
Surface area. Yeah, the surface area is 108 square inches, so that's our constraint, right? So we got to write an equation to that effect. So there's the constraint. What's the equation that pops out of that? Surface area for our situation is 108. What do we get? What is the surface area? How many surfaces are there on this thing?
5.
5. Okay. There would be 6, except it's an open box, and so there's no top, right? So what are, we just have to add up the areas of those 5 surfaces, don't we?
Yeah.
Okay, so what's that gonna be? Bottom is x squared.
Oh, fascinating.
We're
Plus-
finding right now, right?
X, Y times 4.
Oh, good, because the height is y. Each of those rectangular faces, what we might call the lateral faces, the ones that are around on the sides of this thing, are gonna be x by y, aren't they? So 4xy. And then what's that equal to? That's the surface area,
108.
108.
Yeah.
Okay,
Yeah, I'm all over
and
it.
let's immediately, well, okay, so there's our secondary equation.
Yes.
So now, any suggestions what we're gonna do from there? What do you think?
Uh-huh. Oh, gotcha.
Any suggestions?
Solve for variable.
So,
Okay, solve, what do you mean by that?
differentiate.
Okay, we're gonna try to get there, but right now we got a problem. Right now the problem is we've got 2 independent variables in our function. We gotta get it in terms of 1. So how are we gonna use this equation of constraint, do you suppose, to accomplish that? And this isn't
Yeah, solve for
totally
variable.
foreign to you. You've done stuff like this. When we've solved systems of equations, going clear back to like Algebra 1, when you solved linear systems.
Oh, that's wrong.
One of the ways you did that, when you had a system of, say, 2 lines that, both had 2 variables, x's and y's, you solved for one variable in terms of the other and substituted. What do you think?
So Joel, just what you said, like solve for x squared or y,
Okay,
and then plug it in.
and plug it in, good. So we're gonna isolate one of the 2 variables and then substitute that expression that we get on the other side into our primary equation. Now, here's where you gotta be a little smart about this, though. Theoretically, we could solve for either one of these, right,
Yes.
in terms of the other. But oftentimes in practice, there's one that is much, much easier to deal with. Okay, in this case, which one would we want to solve for in the red equation? X or Y?
Why?
Definitely Y.
Yes.
Oh,
Killing
For
it.
sure Y, and it's not even close. How come Y is a much better choice here? Okay,
Yeah, there's no
because,
square
yeah,
root
because in
involved.
this case, the X's show up in 2 different terms, and they're not like terms. So that would be difficult to solve for X. This equation, we would say, is quadratic in X, but it's only linear in Y, isn't it? It's only got a single Y to the first power. And so that Y is really easy to isolate. That's the one that we want to isolate, isn't it?
Yes.
So what, if we do isolate, yes, sir? Well, then it makes it tough. It makes it harder. And what if it were, I mean, I'm honestly probably not gonna give you
Help me solve
something
this.
like that to deal with, but what if it were? If it were quadratic in X also, let's say we decided to solve it for X, then we'd have to solve this thing for X, and we'd probably get 2 solutions in X in terms of Y. We'd have to plug them both in and try them both
that sounds.
and see, it starts to get more complicated, right? Okay, but in this case, we have an easy out. We can solve for Y in terms of X. What do we get if we do that?
You're mistaken. Y equals.
Y equals
Plus.
What-
108.
108
Over.
Minus 4x.
minus
Minus x squared.
x squared. Divided by-
Divided by 4x.
Everybody see that?
Yes.
Everybody see that?
Yeah.
Okay, as soon as you've got your substitution equation, put a box around it. Because in all likelihood, you
What
will
is
be
that?
coming back to that equation. So there's our substitution equation. We're just gonna plug this expression, 108 minus x squared over 4x.
Into
in
the
for
arrow,
Y.
That's what I thought.
And if we do that,
Oh,
we get a new primary equation of a single variable, and that's really all we wanted. So all this stuff we just did was just prep work to be able to do the calculus that we've already been practicing, to make our table, right? Does that make sense?
Yes.
Okay, so now I'm running out of space here, but let's try that. So we end up with volume equals x squared times y. So
X squared.
x squared times that, right?
Oh, there it is. Seems like product rule.
108.
Agreed?
Yes.
Okay, so now let's take that and we'll go to the other page and continue.
Cool.
Yes, I agree.
Okay, so we wanna, when we're, kind of pre-writing this, before we do the calculus, what could we do here? Right now, it's kinda ugly. What do you think? And notice also, we're able to rewrite this now as v of x. We got a single variable, right? That's helpful. Instead of f of x, we just call it v of x.
That's handy.
But right now, that looks like a product and a quotient. Does it have to be that hard?
No.
No.
Could you simplify it down?
Yeah, we can simplify it quite a bit.
Just multiply that by
Well, okay, we can do that. Now look at this also. I've got two factors on the top, x squared times 108 minus x squared. I've got a 4x on the bottom.
Yeah.
So I can cancel like factors, can't I? Because these x's, this x squared is being multiplied by this stuff, I can cancel out an x top and bottom. Does that make sense? Okay, so we can do that helps,
I see.
right? I could distribute the x then if I wanted to also. Why not do that instead of having to do
Why
product
Why
rule?
not?
Why not? I
Right.
like product rule.
Wow.
So I get,
108 x minus x cubed.
You know, that's
V of x equals
okay, good.
108 x minus.
Okay, so there's our function. Now all we have to do is analyze this thing, make a table. But this is a real world situation here, right? And so we also want to know what's our domain? What's the set of values that x could could have, right? Because this is, x can't, for example, be negative, can it?
positive.
It can't be negative because think what it is. It's a measurement, right? The length of a side can't be negative. Okay?
Shoot.
So what is our domain going to be then? Well, let's see. The smallest that x could be, whoops, would be what? I mean, it's
Just
if we look
Just
at our
bigger than
picture,
zero.
this is the part that honestly, I think this might even be the part people have most trouble with, is the domain. Now, if this is how y is related to x, and this is our picture, could x ever be 0?
No.
How come?
Or has it be nothing?
Because,
wouldn't be
okay,
max.
if x were actually 0, then the volume would be 0, right? But the surface area, how's that gonna work? This is one of the dimensions of the surface area,
Yeah.
right? Look what happens to y. If x goes to 0, the bottom of this fraction shrinks, right?
Yeah.
I end up getting 108 on the top, but I get 0 on the bottom, and so y is exploding. Y would get infinitely big.
Yeah.
And so that's an impossibility. Now, could x be really small?
Yes.
Sure, it could approach 0, but it just couldn't actually be
Yes,
0,
yes.
right?
Yeah.
Bigger than 0.
So in our domain,
It's the
that's how we could write the lower limit. X is greater than 0, it can't actually be 0. Now the harder part maybe is how big could it get? What's the biggest that x could get? A lot of times it's nice to kind of look at this picture that we drew and think of it as morphing in your mind. Think of it as changing. Wouldn't you agree that x and y are going to be inversely related? Because the
Yes.
surface area is fixed. We have a certain amount that's set. If x gets smaller, then doesn't that mean that more of that surface area is distributed up and so y gets bigger and vice
Yes.
versa?
yes.
Right.
Mm-hmm.
Okay, a lot of times it's good to look at your boxed equation then, right? Is to think about this in terms of both x and y at the same time. Now, what's the smallest that y could be? And it can't be 0, right? Well, actually, could y be 0 in this case?
No.
As y shrinks down to 0, what's going to happen to x? It's going to get bigger and bigger, right? But that's okay. Eventually, when y goes to 0, that just means that all of the surface area is invested in the base of this thing. Does that make sense?
Yep.
Okay, what is our surface area? 108, right?
Yeah.
Now that would make a lot of sense if we're trying to maximize volume.
Oh.
What's the volume actually going to be when y goes to 0?
0?
It's going to be 0, isn't it?
Yeah.
Right? So that's not going to be our maximum for sure.
Yeah.
But the y could actually go to 0, and it's not like we get some infinities going on when we do that, right? Well, when y goes to 0, we could solve for x down here and see what is x, right? What's the value of x that's going to make y go to 0? We can't see it immediately, but wouldn't that mean that the numerator has to go to 0? Does that make sense? When y shrinks to 0, this fraction has to go to 0, and so we can see that 108 minus x squared would have to equal 0. Make sense?
Yes.
So how would I solve that for x? Yeah, x is plus or minus the square root of 108, but obviously it can't be negative, right? Because that's not in our domain. And so x would equal
Square root of 108.
positive the square root of 108.
Yeah.
Okay, which is just a number. I mean, that's 10 point something, you know. So that's our upper limit of our domain,
Fascinating.
okay?
Yes.
And you can think about it the way we just did, or you could say, well, what would happen if this thing were squashed down so all of the surface area were in the base? You can also pretty easily come to the conclusion then that x squared, the area of the base, would just have to equal 108 in that situation, right? That's as big as we could get. For all the areas in the base, none of it is in the height, okay? So we have our domain. Now all we have to do is make our table, right? We just want to fill in the blanks. Our table's going to look like x, v, v prime, v double prime, and that's the domain. It's going to be in the x row. Okay, but what do we need to do here if we want to? What are we doing? In section 3.5, yeah, we got to get v prime and v w prime, or excuse me, v double prime, right? In order to be able to make our table. So what is v prime? Here's the function. That's a pretty easy one to differentiate.
Oh, yeah, of course. Of course, sure.
What's v prime? We can just pull the 1/4 out front.
Wow, wow. I like quotient rule. Hang on.
What do we get? What's the derivative of 108x? 108
Minus the x squared.
minus
Trace
3x squared, good,
Trace x to the dose.
over 4, right? Okay, and we can analyze that. While we're at it, let's go ahead and get our critical numbers. So is the first derivative undefined for any place in our domain? No. No. Okay, where would it equal 0?
I don't know what
Okay.
V prime would equal 0 when what?
See.
square root
See.
of 108 thirds.
Okay, so yeah, when the top is 0, right?
Yeah.
We can ignore the 1/4, but we know that this fraction is going to be 0 when the numerator is 0. So v prime is 0 when 3x squared equals 108. So let's see, x would equal, what's that going to be? 3 goes into that, so it'd be 16, right? When, no, that's not right. 36.
No.
36.
Not right.
When x squared equals 36, so what's x?
6.
Yeah, we're gonna take it's plus or
That's what
minus,
I
but the
thought.
minus we don't need, right? So we'll just cancel that one out. We just get positive 6. It is our only first derivative critical number
Why isn't it negative 16?
because it's not in
It's a
our domain.
measurement.
Oh.
Because remember, x in this case isn't just a mathematical abstraction. X actually means the width of our open box, so it has to be positive. Okay, let's calculate the second derivative because it's so easy to do, and that's optional in this case, right? All we're trying to do is maximize volume. It's not asking about points of inflection or anything like that. And so we don't really have to do the second derivative, but it's so easy to do that why not? Then we can use the second derivative test instead of the first derivative test. So what's the derivative of the
Never
first
mind.
derivative? Well, derivative of 108, we'll just pull the 1/4 out front. That is
0.
0, good. And so we just get a negative 6x over 4, right?
Yes. Which fact?
Make sense?
Why do you keep the 4?
Because the 1/4 is part of the function. It's being multiplied all the way through, right?
Okay.
Okay, so the second derivative is negative 3/2 x. In our domain, do we have any critical numbers for the second derivative? No, but we don't really care, do we? That's not even really the point. We just want to use the second derivative for the second derivative test. We want to know the sign of the second derivative, which gives us concavity, and our first derivative critical number, right? So now let's populate our table, and I think you'll see that this.
Populate.
The good news is, the functions you deal with in optimization problems are typically way easier than the ones you dealt with in section 3.6.
Good.
right? It's,
Dude,
that part
golden
gets simple,
right now.
it's just the setup and the interpretation of the question that gets a little harder.
Well, you know, that's fine. Problems are easy. Why is V double prime on top?
Okay, so let's put everything in there then. Now, here's our table. Our domain, we said, went from values greater than, and I kind of messed this up. Should that be a rounded bracket there?
No.
Should be square, shouldn't it? Because it actually includes that value, right?
Correct.
So I need to fix that.
Oh no.
Dude, you're dirty.
Okay, so we go from values greater than 0 and less than or equal to square root of 108. We had one critical number that was inside that, which was positive 6, which was a 0 of the first derivative. And what's the sign of the second derivative for any positive value of x?
Negative.
Negative, right? So that's negative. And so what is this first derivative critical number then? We have a horizontal tangent line. Negative second derivative means what? What's that tell you about the concavity? Yeah, it's frowny face. It's down, isn't it?
It's sad.
So it's a sad function. So that's our maximum, right? And so all we needed to know then in this one was what are the dimensions? Well, the x dimension is 6, right? It never even really asked for the volume. We don't need to know the volume. We could. If we wanted to know the volume, we just fill in that blank right there, don't we? Right? We just plug 6 back into the original equation. But we just need to know the corresponding y value to get the dimensions. Where do I go to find that? Yeah, go back to the boxed equation. That's why we put a box around it, right? So then y would just equal, 108 minus
Not gonna happen.
6 squared over 4 times 6, so 108 minus 36, what is that, 72 over 24 is 3. So we get 3 for y, and so we know the dimensions. The dimensions would be x is 6, y equals 3. Okay. That's how we will maximize volume for our given surface area with a square base.
That's something, dude.
Now you can see how that's important. If you really did want to design this so you were maximizing volume, then you have to do a little calculus to find out. All right, let's try maybe one more of those, because this just takes a little practice.
It's not gonna happen.
Let's try, how about,
Honestly, one of them was great.
we're down to, what are we doing? Oh, today's the short day, isn't it?
Yeah. Seis minutos.
Yeah.
Monday, there's no more football.
It's true.
There is no football, that's right.
Monday,
How about this
basketball
one?
time.
Let's go, March Madness.
Dude, let's March Madness. Dude, Zona's been hot. So
That's
Syracuse. Syracuse got lucky.
Syracuse got very lucky.
Yeah.
It was really funny because they were talking about Iowa State. Iowa State went into the game against
Yeah, I know.
Kansas.
Railed.
They're like, he's just giving a good.
Okay, what about that? Find two numbers whose product is 192 and whose sum is maximum. Okay, you can't really draw a picture for this one, right?
Yes, you can.
So what's our, so really step one doesn't do much for us here. Our numbers we'll just call, how about x and y?
Yep.
So we jump to kind of the step two. What's our primary equation then? What is it that we're trying to maximize?
XY is 192.
No, that's not what we're trying to maximize.
Oh, the
The sum, okay.
Plus Y equals
So step two, we'll call it S for sum, is what?
X plus Y.
X plus Y. Okay, how many independent variables do we have?
2.
2, so we need an equation of constraint.
Yes, we do.
Okay, if we didn't have an equation of constraint, I would just pick numbers that approach infinity and my sum would be pretty big, right? But we do have a constraint. What is our constraint? Yeah. Okay, what's 192?
XY.
The product. So the
Yeah.
equation then would be xy equals
192.
192. Now, in this case, does it make any difference which variable we solve for?
No.
No, it's totally symmetrical, doesn't make any difference. We'll just solve for y, how about, arbitrarily, doesn't make any difference. So y is 192 over x, right? That's the substitution we'll make. And so we end up with then, the sum equals x plus 192 over x. Okay. So, what are our constraints here?
X can't be 0.
Okay, so the product has to equal 192. If the sum is going to be as large as possible, what's our lower limit going to be? Can x be 0?
No.
Can't be 0, can it? Give me some reasons why. And you can kind of talk about this sort of almost philosophically or conceptually, or you can point to something concretely and say, nope, the math gods won't allow it because of that.
Y equals 192 over X.
Okay, anything times 0 equals 0. Good. And so, sort of philosophically, we know that we couldn't get 192 for our product, could we?
No.
Mathematically, what can I point to up here and say, oh, red flag, x can't be 0?
The boxed equation.
Yeah, there's an x at the bottom right there, isn't there? Right?
I
You
like
can't
the
divide by
boxed
0.
equation.
So our domain, then, if we look at the domain of this thing, we know x has to be greater than 0, right? Now, what's going to be the biggest that x could be? Well, as x gets big, y gets small, right? Does that make sense? Okay. So, as y gets small, as y approaches, but y can't be 0 either, can it?
No.
What behavior of x would cause that? Because we already told me these two numbers are interchangeable. We just called one x and one y arbitrarily, but they're just two positive numbers, right?
Mhm.
So as y shrinks down to 0, based on this equation, what would x have to do to make that happen?
It's super big.
It'd have to get really big, wouldn't it? So is there a limit to how big x could be?
No. No.
Not really, is there?
No.
Right? So x would approach, I want to do sum as maximum. I guess so. Okay, something like that. Right?
Mhm.
Make sense?
Yep.
Okay. And so now we just do our calculus. What does the derivative look like? What's s prime look like? 1. And that's 192x to the minus 1, isn't it?
Mm-hmm.
So what's the derivative of 192x to the minus 1?
Negative.
Negative 192
X,
X to the
negative 2.
negative 2. Right? Okay, are there any critical numbers?
Yes.
Are there any places in our domain
Oh.
where the derivative is undefined?
No.
0, but 0 is not in
Not
our domain, is
included,
it?
yeah.
Okay, to be continued. Yep.